So here we've got a differential equation and our aim is to solve for the original function y. So unlike the first order differential equations, this one doesn't actually work with the particular integral method because we've got a second derivative here. So I've classified this differential equation as second order linear homogeneous and with constant coefficients. I'll go through what those actually mean at the end of the video. For now, let's focus on actually solving this. Now it might seem tricky at first, but the process is actually quite simple. So we have a linear combination of y and its derivatives. Now if you think about what function could actually give us something like that, e to the power of x would be the first one that comes to mind. So we can say that y is some form of e to the x, so we can say a constant times e to the power of another constant times x. So now if we differentiate this, you should see that we get another multiple of the original function. So dy dx is equal to am e to the power of mx. So see, we've got a multiple of the original function y because we can write this as m times ae to the mx. And then similarly for the second derivative, d squared y over dx squared, we can say that's equal to am squared e to the power of mx, which is equal to m squared times ae to the mx. So here we've shown that each derivative is just a scalar multiple of the original function, which means that we can plug these into the original equation that we had and try and see if it will work. So let's plug those in. So d squared y dx squared is the first term. So m squared times ae to the mx. And then we have minus 3 dy dx, so minus 3 times this expression. So minus 3 times m times ae to the mx. And then plus 2y, so plus 2 times the original function. So plus 2 ae to the mx. And I can write this in brackets just to make it a bit more simpler to see what the next step will be. So now we can see that we've got our linear combination of differentials and functions, and now we can see that we can divide through by ae to the mx. So that means that this function was valid. So we can divide through, and then we'll get m squared minus 3m plus 2 is equal to 0. Now what this has actually shown us is that we can solve for the constant inside the power of the exponential by using this equation over here. So if you just plug in the differentials to the original equation, then you can get an expression in a quadratic form of the powers constants. So now this is called an auxiliary equation. So an auxiliary equation basically helps us to solve for the general solution of the original function y. So if we factorize this expression, then we would get m minus 2 times m minus 1 is equal to 0, which gives us m is equal to 2 or 1. Now this is actually given us two values of m, which means that we're going to have two different solutions. So we can either have ae to the power of 2x, or we can have ae to the power of x. But since both of these are valid, we can then say that it's going to be a sum of both of these. So we can say that our function y is equal to a sum of both of these expressions. So we can say that y is equal to ae to the power of 2x plus be to the power of x. So basically what this is saying is that some linear combination of these two functions gives our original function y. And the reason that works is, as I've shown before, when you differentiate this, you just get a multiple of the original function y, and then if you plug that into the original equation, then you'll be able to factor out that original function and then solve for the roots. So this is called the general solution. So this is the general solution because it's the full solution of the equation, assuming that you haven't got any boundary conditions. So boundary conditions are basically where you can solve for the coefficients a and b, but I'll go through that in the next video. So this is the main basis of it. So all you do is find the function you need to plug into the equation and then solve the auxiliary equation. Now, when you do differential equations, you can write out the auxiliary equation straight away without having to do all of this derivation. This is just here to help you understand how it works. So when solving differential equations, you can literally just jump straight to the auxiliary equation by looking at the differential equation. So by looking at this method, all you need to know is that to go from here straight to there, you look at the power of the differential. So if it's second order, then you put m squared. And then if it's the first order differential, then you put m. And if it's just the original function, you put a constant. And then that's how you can get the powers of the functions that you use to get your general solution. So as I said at the beginning of the video, I'm going to go through these classifications of this differential equation. Now, strictly speaking, you don't actually have to literally write down it's homogeneous, it has constant coefficients. You just need to know these as a way of classifying different differential equations to see which type of method you can use. If you know which method to use, you don't really have to remember this, but it's good to remember just so that you can know the difference. So it's second order because the highest differential power is second. So we can say that the highest differential is d squared y over dx squared, which is why it's second order. It's linear because all of the differentials and all the functions are to the power of 1. So there's no higher powers than 1 on y or dy dx or d squared y over dx squared. So we can say that there's no y squared or dy dx squared, etc. It's homogeneous because the whole equation only depends on y and its derivatives. If we had something on this side of the equation, something like sine x or x to the power of some constant, then it would be non-homogeneous. So this is homogeneous because it only depends on y and its derivatives. And it has constant coefficients. That's pretty obvious. There's no other coefficients in front of d squared y dx squared or dy dx or y. So for example, the integrating factor method is not an equation where you have constant coefficients because you obviously have the f of x times y in the middle. So that's why for the integrating factor method, it's specific to use because of the fact that there aren't constant coefficients. But with second order differential equations, you won't have to deal with that.